Here we are, Unit 4, Lesson 1.3. It's the law. So in this part of the lesson, we're going to talk about Newton's first, second, and third laws of motion. And then another essential question is, how is the law of force and acceleration applied in everyday situations? So the first question talks about, as you read, underline examples of objects affected by inertia. So first we have to talking about Newton's first law. Newton's first law states an object at rest stays at rest and an object in motion stays in motion at the same speed and direction unless it experiences an unbalanced force. So an object that's not moving is going to sit there until the forces on it are unbalanced. A ball will continue rolling on the floor until the forces are balanced. And so remember, you have the force of friction going against the motion of the ball. So let's look at our reading. And so it asks you to underline examples. And so a chair will not slide across the floor unless a force pushes the chair, and a golf ball will not leave the tee until a force pushes it off. So that's the example you were supposed to underline. The next one asks you to look at the magician in the bottom. And it says, do the dishes on the table have inertia? So you got to remember inertia. It's going to stay at rest unless acted upon by a force, and it's going to stay in motion unless acted upon by a force. And so do the dishes have force on them? Yes, they do. And so the dishes do have inertia. And if we look at the illustration, you can see that the musician snaps the tablecloth and that the dishes do not move. So the trick in this is to have a tablecloth that doesn't have a lot of friction and to pull straight down. And the little kid that the bookshelf fell on, he's okay. So we're going to watch this video with Steve Spangler. Oops. Don't try this at home without your parents' permission. Again, don't try that at home without your parents' permission. Okay, next question. The question asks you to infer. And remember, does it mean to make an inference? It means you're going to make a statement based on your previous knowledge or things that you've read and have knowledge about in your head. So, what forces acted on the test dummy to stop its forward motion? Oops. So, remember that the car is going to continue going forward. And so when it stops, when it hits this barrier, the dummy is going to keep going forward. And so for safety's sake, we want to stop that forward motion. And so we have the force of the seat belt that acts against that forward motion, and we have the force of the airbag that acts against that forward motion. So the dummy is going to keep moving, even though the car has hit the wall. So it's going to keep moving, and we want to oppose that movement. And so the seatbelt is opposing that forward motion, and the airbag will be opposing that forward motion. The next question, identify. As you read, underline Newton's second law of motion. So the second law of motion states that acceleration of an object depends on the mass of the object and the amount of force applied. So this is more or less just F equals ma again. So in this example, there are players that are training to push a massive object. If the players push with a force of 150 newtons and the object has a mass of 75 kilograms, what is the object's acceleration? And remember that 1 Newton equals 1 kilogram per meter squared. So remember in problems that we are going to write what we know. So we know that we have, oh my goodness. We know that we have 150 kilograms. That's our mass. We know that our force is 150 newtons. And we're going to use the equation F equals ma. Now the problem is that we are not solving for F, we're solving for A. And so to get A on the side of the equation all by itself, if you remember from your math class, you're going to divide both sides by M, and we end up with F divided by M equals A. So you have to show where you manipulated the problem for the variable that we want to solve for. So the force is 150 newtons over, did I write something wrong? Oh, yes, I did. The mass is 150 kilograms. See, that's why you always write. That's why you always write what you know. Okay, time to argue with me. It really doesn't like me today. So we have 75 kilograms. Sorry about that. So we divide that, we end up with 2 meters per second squared. Remember that the units for accelerating are meters per second squared. Now, if you wanted to look how we ended up with those units, we would start with just leaving our equation the way it was. So we'd have 150 newtons. And we know that, sorry, so we know that we can break down this unit to 150 kilograms per meters per second squared equals 75, oh goodness, 75 kilograms times our variable acceleration. And we do the same thing. We divide each side by mass. It cancels this out. And then we divide this in here and we get 2. And then this unit cancels out because it's on the top and the bottom. And then we end up with 2 meters per second squared. So this is just to show you how those units canceled out. Okay, now we have another problem. In this problem, more mass is added to add a little bit more challenge to the football players' workout. So we start with F equals MA, and we know that the mass equals 160 kilograms, and the force equals 150 newtons. So inside, you have to show your work. So you could show the equation, give the values that you know, and then we're going to manipulate the formula to solve for the variable we want, which is acceleration. So we divide each side by the mass, and that gives us force divided by mass equals acceleration. And then we plug in what we know, and so we have 150 newtons divided by 160 kilograms, and that's going to give us that acceleration equals 0.91 meters per second squared. And we give it a circle. So if you want to see how that works out in terms of algebra, to see how those units cancel out, we'll do that up here. So we have our force, which is 150 newtons, equals 160 kilograms times acceleration. So we know that we can change this unit, break it down to 150 kilograms per, oh my goodness, stop, go back. I don't know why PowerPoint did this. I don't know how to get it to go back. I don't know what happened. So we get this as meters per second squared. So force equals mass times acceleration equals 160 kilograms times acceleration. We take both sides and divide by 160 kilograms to get acceleration on all by itself. So this cancels out and this cancels out. We divide 160 into 150, and that gives us 0.91. Kilograms is on the top and on the bottom, so it cancels out, and that gives us our answer of 0.91 meters per second squared. This is just to show you the algebra in case you're interested. Okay, 17 has 3 parts. So they want you to look at the truck, and the dude's truck stalls, and he is going to try to push start it to get it to going fast enough that he can jump in and pop the clutch, if you know what that means. And so you have 3 scenarios. You have him with the truck fully loaded, and then he's going to take off some of the mass off the truck, half of it, and then he's going to empty the truck completely. And so they ask you to calculate the acceleration of all 3 scenarios. So we're going to start with a truck has a mass of 1,500 kilograms and is loaded with 1,000 kilograms of furniture, and we want to know the acceleration. So what do we know? We know that uh, the mass, I don't know why it does this. The mass is going to be 50. I love Microsoft. Microsoft is my friend. Is going to equal the fifth. I'm not touching anything. Oh my goodness. Is going to be the 1500. Okay. Okay, computer. Going to be the, please play nice. Why is my computer against me? Going to be the 1500 plus the 1000 to get the total mass. So we know that the mass is 2500 and that he has to apply a force of 8.2 newtons. So we're going to use our formula, F equals ma. And so we substitute in our mass is 2500 kilograms. Sorry, we have to derive the formula first, don't we? So we have to manipulate the formula to get acceleration all by itself. So we divide each side by the mass, and that gives us F divided by m equals A. And so we have a force of 8.2 newtons divided by 2500 kilograms. And that's going to give us 0.03 meters per second squared. So that's the acceleration for the truck fully loaded. Next is if he has the truck halfway loaded. So we know that the mass is going to be the 1500 kilograms of the truck. Oh, we're off. Going to be the 1500 kilograms of the truck plus the 500 kilograms of the furniture. So the mass is going to equal 2000 kilograms. We know that the force is equal to 60. Pretty sure that's supposed to be 6.6. Let me look. Sorry, it wasn't 8.2 in the previous one. It was 82. So the force is 66 newtons. And so we manipulate our equation, F equals ma. Divide each side by m. Remember, you have to show this step. So F divided by m equals A. And so we get 66N divided by 2,000 kilograms. And that's going to give us an acceleration of 0.03 meters per second squared. Okay, now the last scenario, he totally empties out the truck, so we don't have to add anything here because he doesn't have any furniture. And so the mass equals 1,500. The force equals, what does it say here? 50 newtons. We write our equation we're going to use. We manipulate our equation. We're solving for A, so we divide by M on both sides. So we have F divided by M equals A. So our force is 50 newtons divided by our mass, which is 1,500 kilograms. And that gives us 0.03 meters per second squared is our acceleration for the third scenario. And now we're ready for part B. Part B says to plot the data from your three scenarios on the graph. So the first thing you have to do is you have to determine what the intervals are on the graph. So what I always do is I count off tens very first thing. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. So for my mass, I know that I'm going to have to go up to 2,500. So if I went by a 1,000, I'd have 1,000, 2,000, 3,000. So that works. So if I put 1,000 kilograms here, 2,000 kilograms here, and 3,000 kilograms here, that works. I can encompass all the masses that I am going to use to graph. And then my forces range anywhere from 82 to 50. And so I have 3 spots to plug those in on. So I can't do 25, 50, and 75 because that wouldn't get me high enough for 82. So what if I went 50, 100? Or let's see if they're each one. Actually, we could do 82 up here at the end, right? No. So let's make this 100 and make this 50. That way I can ensure that I make sure I have all my strength. And so 82 wouldn't fit if I went 25, 50, 75, because 82 would be up here. So I have to use a smaller increment. So let's graph the first one. We have 1,500 kilograms. For first thing we need to do is figure out where that would be. So here's 1, 2, 3, 4, 5. Here's 1,500. And the amount of force I have there is 50. So I want to find out where 50 and 1,500 go together. And that's where my first point is going to be. And then I'm going to do the scenario where he only had half of the furniture on the truck. And so I know I'm going to be at 2,000. And my force there was 66. So here I have 51, 52, 54, 56. So I want to find out where 56 and 2,000 meet. That's going to be where my next dot is. And then I'm going to do the scenario of the fully loaded truck. And there I have 2,500 kilograms. So 22, 24, so this would be 25. So I'm going to find out where 25 and 82 meet. So here's 52. I'm sorry. Did I do that right? 1, 2, 3, 4. So 50, 60, I didn't do that one right. 8. We need 2066. See, that's why you always check your work. I don't know how to erase with PowerPoint's doohickey thingy. That's not what I wanted. So sorry about that. I was trying to go too fast. Okay, so here's, I'll put these on here so I won't make the mistake again. Okay, so we had 66. So halfway between and a little bit more. So 66 and 2000. Sorry about that. I wasn't paying attention close enough. Okay, so then we take it to our third scenario, 2500, and we want 82. So not quite 85. So there's my 3 points. So here we have the mass of 1500 and the force of 50. Here we have the mass of 2000 and a force of 66. And here we have the force of 2500 and 82. So sensitive. And so we're going to connect our lines with our best fit line. And there's part B. How much fun was that? So then we go on to part C, which says, how does the amount of force needed to accelerate an object relate to an object's mass? State your claim and use the graph as evidence. And so one thing you have to say is that as you increase the mass, what happens to the force? And that means that there is a relationship between mass and force, and you describe it. And then remember that it says state your claim using the graph as evidence. So that means you have to talk about the graph. So the graph shows, and you're going to talk about what it shows in the graph. Okay? So that gives you that question A, B, and C. Okay, question number 18 says the arrow below represents the action force exerted by the swimmer. Draw an arrow that represents the reaction force. So you're going to want to write an arrow going this way. Okay, let's go to the next question. 19. Label the action force and the reaction force in the image below. So this kind of goes along with for every action, there's an equal and opposite reaction. And so we have a ball falling to the earth in the first image. So the action is that it's falling to the earth, and the reaction is that gravity is pulling on it. If we look at the next question, it is a CAR. Can Earth's gravitational field exert a force on object not in contact with Earth? Use evidence and Newton's laws of motion to support your claim. So I'm going to give you some examples. So here we have the comet example, where the sun's gravity changes the projectile of that comet. And then we also have the space debris that's left out up into space around Earth. So these are broken down satellites. These are when satellites collide and those parts stay in orbit. They can have a collision in which there's enough force to cause that object to fall back onto Earth. And so the Earth's gravity keeps these pieces of junk we put up there around Earth, just like the moon. It's trapped by the Earth's gravity. You can also think of this as if we throw a ball up into the air, nothing's touching that ball. So if the Earth wasn't acting upon it, the ball would just keep on traveling up and up and up into space. But Earth's gravity is pulling that ball back to Earth. So, can Earth's gravity exert a force on objects that aren't in contact? So you just there had 3 examples.